So yesterday we put a circuit together with an inductor and a resistor, an RL circuit. But we'd also mentioned capacitors. We did resistor capacitor circuits. Well, now we're going to put the inductor and the capacitor together. So without giving any charging details, let's say we have a fully charged capacitor. So I don't know why I just switched pen colors. This is a fully charged capacitor. And we are then going to connect it in a circuit with an inductor. So probably it makes better sense to say we have the circuit set up and then we apply a potential difference across the ends of this capacitor to make it fully charged while this is open so that there's nothing involved over here. So now we have a fully charged capacitor. So this plate has a charge of positive Q, this plate has a charge of negative Q. Because there are extra electrons on this plate, there are missing electrons on this plate. And exactly the number that left here ended up here. That's why they're always equal. Well, now we're going to close the switch. When we close the switch, current tries to flow clockwise. Because, remember, there's no resistance in this circuit. It's just a bare wire, though it's a coil, and we'll come back to that in a second. But because it's a bare wire, if this switch is closed, these electrons now have a way to get back to this positive plate. There's no potential difference. There's no battery over here anymore holding them separate. These are now wanting to be, we want to cancel out. This doesn't want to be charged anymore. So this would discharge. However, the inductor says, oh, I don't think so. I do not want current to flow. But it eventually loses. And we have current flowing this way. So eventually we reach the stage, and I'm not gonna, the switch is closed. We reach the stage where Q is 0. There's nothing charged here. But there's been current flowing through here, and the inductor says, you better keep it going. I do not want a loss of current because I do not want a loss of magnetic flux. So it's gonna keep this current going. But if the current keeps going, remember current is the flow of positive charge, the direction of the flow of positive charge, if that's what was happening. If it keeps going, well, now these imaginary positive charges are going to end up on this side. So we have, because the current's going this way, we have a buildup of positive charge and negative charge. Well, once you get to this full charge, you can't keep current going anymore because this capacitor cannot hold any more charge. Another way of saying it is all the energy is transferred and there's no current anymore. Well, now we're in the same as the original situation right after the switch was closed, just backwards. So now current's going to flow the other way. And then the inductor keeps it going. So even after this fully discharges, it's going to push charge back to, and the top side becomes positive again. And then current's going to stop. But then current stops, so now current flows this way to discharge this capacitor, but as it's completely discharged, there's current flowing, so current keeps flowing, and it's going to take it back here. So we get a cycle. And what I like about this picture, I don't know how I'm going to get this under this textbook very well. So that's what we have here. We have an electric field in the capacitor, and then we start to build up current flow, and then we have a magnetic field in the inductor, but then we start to build up charge the opposite direction. This is really not working. And then because there's charge the opposite direction, we're going to get it fully charged, but now it's going to discharge by current flowing the other way, and we get magnetic energy, and then it tries to keep it going, but it's starting to charge it, and we get back to the original conditions. So what we're going to have is over and over and over, capacitor fully charged, no current in the inductor, lots of current in the inductor when the capacitor is discharged, but that's going to recharge the inductor, which is going to start it over in the opposite direction. So we have an oscillation. Oscillation. So if we apply the loop rule to this original capacitor, so as we go around the loop clockwise, we gain potential as we go across the capacitor, and then we lose it across the inductor, so minus VL. And we finished our loop, so that's equal to 0. So I'll remind you that capacitance is Q over V, and for an inductor, EMF is negative L di dt. So Q over V minus this, this loss already has this negative sign included. So I'm not going to copy the minus sign also. L di dt equals 0. So this, I wrote that wrong. We were solving for V. We need Q over C. I am so sorry. But I'm not restarting for that. So now we can rearrange this. And we have Q over C equals L di dt. Now I want you to remember that current is the derivative of charge, which means that di dt is the second derivative of charge. And now we need to introduce a negative sign, because as this current is flowing, we get positive current flow if this is the positive direction, because this charge is decreasing. So as one is increasing, the other is decreasing. So I need to introduce a negative sign. So di dt is negative d squared q dt squared. So now I can put this in here. And I can write Q over C equals negative L d squared Q over dt squared. So one last thing, I'm going to isolate this term here. So I'm going to divide by L, move the negative sign to the other side, and I'm going to reverse the way I'm writing. No, I'm going to leave it the exact same way. So I'm going to have negative Q over LC equals the second derivative with respect to time of Q. Now I want you to hold on to that while I remind you of an old thing. If you have a mass on a spring, you know the mass oscillates back and forth. Because the spring force depends on the displacement. So if we do Newton's second law, net force equals mass times acceleration, the force from a spring is negative kx, and it's negative because it's in the opposite direction of the displacement. Well, acceleration is the rate of change of velocity, and velocity is the rate of change of position. So acceleration is the second derivative of the position. Notice it's almost this equation. So if I finish rearranging it, solving for the second derivative term, oops, I forgot my squared, we have negative k over m times x. Now, when we encountered this before, we said we're going to guess a solution, and we guessed correctly that x equals a cosine omega t plus phi, phase constant. A was the maximum displacement, the amplitude. We have a cosine function. We could have guessed a sine. It would have worked just as well, but the College Board chose cosine for their formula chart. And then over time, the other description is this omega, which is angular frequency. Remember that angular frequency is measured in radians per second. And it's related to two other things. Angular frequency is equal to 2 pi times regular frequency, which is measured in hertz. And frequency is 1 over the period. So, very brief first semester review of something at the end. But the reason I bring this up is because notice we have the second derivative of something, and a negative and a constant, and this was our solution. So if we match this up, we have the second derivative of charge equals to negative something times q. So omega was this part here, this k over m, for this situation. Let me squeeze this in here. Omega equals k over m. Omega squared equals k over m, excuse me. That's why it's a square root. So for this situation, we would have the same form of the solution. Q would equal Q max times cosine of omega t plus phi. And omega is equal to the square root of the thing between the negative sign and the q, which is 1 over LC. Now we would usually write that as take the 1 out of the square root. So a while ago, as I was introducing LC circuits, I said we're going to have back and forth. It's going to be charged, the magnetic energy, which is going to charge it to charge the other way, capacitor to charge the other way, which is going to make current flow the opposite way, and the inductor keeps the current going, and so the capacitor charges the original way, which is then going to discharge, putting current through the inductor, and over and over and over, and it's going to cycle at this angular frequency. So physicists and mathematicians like angular frequency. Most of the time when we do problems, we don't want angular frequency. We either want regular frequency in hertz, or we want a period. So your first couple of problems are going to deal with that. Now something else I want to talk about, and again is similar. I just redraw the circuit here. So we have our capacitor and we have our inductor. And we have, at some point, we have a maximum charge, and at later, we have a maximum current. Well, we know a capacitor stores energy. We have the capacitance stores energy 1/2 QV. Often, because we don't want to have two things that are changing, and we don't have any voltage in this problem, or, well, we could, but we could also use 1/2 CV squared or Q squared over 2C. They all have their uses, but this is the energy stored in the capacitor. Well, as that charge drains away, so easiest to see from this equation, as the charge drains away, there's less and less energy stored in the capacitor, but there's current through the inductor. And you now know that energy stored in an inductor is equal to 1/2 L I squared. So as there's more and more current, as the charge is discharging, there's going to be more and more energy. Once you have lots of current, this is fully discharged, all the energy is in the form of magnetic energy, but that keeps the current going, the inductor keeps the current going, which makes this back into charge. So we have an oscillation between these two forms of energy. When you have maximum charge, all the energy is in the capacitor. When you have maximum current, all the energy is in the magnetic field in the inductor. So this again, if we go back to our mass on a spring analogy, remember we had an interplay between spring potential energy, so stored because of its position, and kinetic energy. So this is charge on the plates of the capacitor. This is similar to the spring potential energy, because spring potential energy is a storage because of location. This is storage because of the location of the charge. Kinetic energy, just 1/2 kx squared, so the position. Farther away, the more energy stored. The more charge on those plates, the more energy stored. Magnetic energy in the inductor is stored because of current. Well, current is movement of charge, movement of location. That's like velocity. So this is similar to kinetic energy, 1/2 mv squared, because velocity is things moving. Current is charges moving. Charges past a particular point of time. So just like a mass on a spring was converting continuously kinetic and spring potential energy back and forth, this kind of circuit is converting electrical energy storage and magnetic storage. Or it's not really storage then because it's movement, but same idea. So we have an energy back and forth, and we have omega for the oscillations is 1 over the square root of L over C. So why am I teaching you this? Because you like to listen to the radio. Radios have to be tuned to a particular frequency. You do that with this kind of circuit. This is included in a radio circuit. Usually nowadays it's done with a fixed inductor. You have a solenoid that you put in the circuit and it has a particular value. And then you could have put in a capacitor in the circuit. And when you change the spacing of the capacitor in between, you're changing the capacitance, which means you're changing the angular frequency of this circuit. So you match your angular frequency of the radio in your car to the frequency of the radio station that they're sending out. If they match, you will pick up that signal and be able to listen to it. If they don't match, then you don't pick it up if you're in between radio stations. So on old cars, you actually had a dial. And when you were turning the dial that little tiny bit, little bit or more, that was physically changing the spacing. Now that we have electrical radio, digital radios, most of the time it's not a physical change in the spacing, but it's still changing something about this kind of circuit. This is how you tune a radio. So that's it for this video. There's going to be one more video today. You must watch them both.